Welcome to EDU World Space.
Okay, so we have a spacecraft that's in orbit around the moon. It experiences some kind of electrical malfunction and it starts falling, right? So we want to know what its final velocity is when it's about to crash on the surface of the moon. So if this is the surface of the moon and we have a circular or spherical spacecraft, if you will, right before it crashes, then we have velocities in two directions, right? We have this one, which I'll call in the x direction, that's v sub x, poorly written, but nonetheless, and a velocity in the downwards direction, which I will denote as v sub y. Now we know this because we have an x direction velocity component from when it's orbiting the moon, and we pick up this y velocity component because the moon starts pulling it downwards, right? Now we know that its total velocity is going to be related in this way. It's going to be the square root of vx squared plus vy squared. Pythagoras theorem, just trying to find what its total velocity is as it's about to crash, right? So we need to find two variables. We need to find v sub x and v sub y to figure out what this answer is. To figure out v sub x, we can start with the fact that we know that the spacecraft is in orbit. Alright, so let's start there. It starts in orbit, I should say. Not that it is throughout the entire problem, but it starts in orbit, and its orbital velocity, given to us in the chapter, or you can derive it yourself, either way is fine, is the square root of g times the mass of the moon, which I'm denoting with a little m here. This is not m times m, this is m subscript m, to say that it's the mass of the moon and not of our spacecraft. And that's being divided by the distance between the spacecraft and the center of the moon. Now you might notice that this distance is going to be equal to big R, which I've labeled over here as the radius of the moon, at 1.74 times 10 to the 6 meters, given to us in Appendix F, plus the 50,000 meters that it is above the surface, because that is its total distance from the center of the moon right here, right? And the reason I changed this to meters is so that I'm not adding a million something meters to 50 kilometers, because you can't add things unless they're the same units. Also, it's very good to work in SI units all the time, right? So R is equal to big R plus 50,000. Now we know what G and M sub M are, looking at Appendix F, and we can plug in and find what I will call Vx, which is going to be its x velocity while in orbit, right? So when we plug those numbers in, you get 1655.3 meters per second. I'm just going to keep it to one decimal to, make it clean. I know this is in meters per second because all of my units were in SI when I plugged them in, so an SI unit will pop out, right? Also, you can do unit analysis in case you're not sure. But we know that this is in meters per second. And we're also told in the problem that the malfunction causes it to lose 20 meters per second. So we're actually going to take 20 off of this because of the malfunction that causes it to crash. So that gives us 1,635.3 meters per second. And that is what we're going to be able to plug in for v sub x right there. Because we know we've already done all of our analysis in the x direction. This is it. This is the whole analysis in the x direction. There's no more to be done, and any analysis to find what's in the y direction is not going to have an effect on the x direction's velocity. So we know nothing else is going to change, and this is our v sub x for good, right? So one thing solved. Perfect. Now we need to figure out what in the world is v sub y. That's a question mark. So we need to find v sub y. So let's go to page 2 and try to figure this out. So in dealing with the y component of the velocity, in other words, in dealing with vertical motion, we can ignore what happens in non-vertical motion, which means that instead of looking at, give me my pen, instead of looking at an object that's orbiting the moon, I can simply look at this as an object released from really high that falls straight down. And when I find that velocity, that'll be the same, that will be what Vy is. It will be the same value, because anything that happens in this orbital direction has absolutely no effect on what happens in its falling or y direction, right? So we need to figure out how to find the velocity of an object dropped from that height. Now, we can figure that out in a not too tough way. So we know that potential energy is given, or you can derive this yourself, as I said that earlier too, but I do always encourage deriving things, but it's defined in there as negative g times the mass of the moon times the mass of our spaceship divided by the distance. Now, we're dealing only, or not that we're dealing with, we only care about the magnitude of our potential energy difference, which we're going to find, right? And I'm going to explain a little bit of that. We want to find the difference in potential energy between right here and right here. We want to find delta PE, or the difference in potential energy. And the reason we do that is because we know as an object falls, it converts potential energy into kinetic energy. So we want to find how much potential energy gets converted to kinetic. Now, this is where the magnitude thing I mentioned comes into play. Since we're transferring things into kinetic energy, we don't need to worry about what's positive or negative. We can simply look at the magnitude, or the absolute value of what we're dealing with. And that's going to be just g times mass of the moon, mass of the spaceship, over its final distance, or r final, minus g times mass of the moon, mass of the spaceship, over r initial. Which you can go on to further factor out g mass of the moon and mass of the spacecraft, and leave us with a simple fraction of 1 over r final minus 1 over r initial. So from here, you may run into one issue. It's, these are constants, we know that. These we can figure out by looking at the problem, but we don't know what the mass of the spaceship is. We're going to ignore that for now, because we just want to see if maybe we don't need it, right? Maybe we don't, or maybe this cancels out somewhere, which, spoiler alert, it does. So what's its final distance from the center of the moon? Looking at our original picture, we see that its final distance is simply the radius of the moon itself. And its original distance, r naught, is going to be the radius of the moon plus that 50,000 meters, which we did right here. And we can just plug those in. And, well, yeah, you can plug them in right now just to get a value for this. But what I'm going to do prior to plugging anything in, because I am personally not one to like plugging things in until I know that I don't need to worry about this, because again, we don't know what it is. So what's our next plan once we even figure out all this? Well, like I said, it gets converted to kinetic energy, right? So it's equal to kinetic energy. Which means that, so a little arrow means that g m little m times mass of the spacecraft times 1 over r final minus 1 over r initial, ooh, that's a terrible r, but it's an r, trust me, is equal to 1/2 mv squared. Oof, there we go. Oh, I'm sorry, you can't quite see that. So it's equal to 1/2 mv squared. Now this m is the mass of the spacecraft, right? So since they're equal, we can actually divide out the masses of the spacecrafts. And let's add a page. That means if you just move everything over and solve for v, which, by the way, I should have clarified, this v is vy. It's the velocity in the y direction. So we actually get the square root of 2g mass of the moon times 1 over our final, which, again, its final is just the radius of the moon. So, in fact, I can just replace that here, right? Its final position is on the surface of the moon at r, big R, minus 1 over r plus 50,000. Oof, writing's getting worse. Square root extends all the way over there. That is equal to Vy. So now that we know what all the numbers are, now we can plug in and get a numerical answer. Which, if you plug all those into your calculator, you should get something around 396.8 meters per second. So we know what our Vx is, we know what our Vy is. Now we just plug in to the velocity formula. V equals square root of 1635.3 squared plus 396.8 squared. And that will give us an answer that is, let's see here, so 1635.3 squared plus 396.8 squared. So that's equal to 1682 we'll round up and say 8 meters per second. Now they want kilometers per hour. Now, a simple conversion from meters per second to kilometers per hour is just multiplying by 3.6. And if you can't see why, let's go ahead and do that here. So meters per second, we want to change meters to kilometers. So we want 1 kilometer is 1,000 meters. So that those meters will cancel out and we'll get kilometers. And then we want hours out of seconds. So 60 seconds in a minute, 60 minutes in an hour. So 3,600 seconds are, that's an S, not a 5. 3,600 seconds are in 1 hour. Now, you can just combine these two, and you see that, 2 zeros cancel out in each one, and then that 0 moves that over, and you just get 3.6 is your scaling factor, right? So you take your answer, you multiply it by 3.6, and you get about 6058. I was about to do a 7, but I'm rounding up. Kilometers per hour. That is its total velocity right as it crashes on the moon's surface.